Okay, we're gonna go ahead and get started. This is Expeditious Code via Inference. I'm Mike Fikes. Hopefully you're enjoying the conference so far. A little bit of background about me, really quickly. I think I'm kind of an anomaly in the ClojureScript world. I came in without a web development background. I've always been interested in mobile apps. And that also kind of got me interested in contributing to the ClojureScript compiler. I started doing that a few years ago. These days I use ClojureScript and React Native. That just makes things so much easier to do. I've also taken an interest in self-hosted ClojureScript, so I'm behind things like Plonk and Replete. I work at VOUCH, where we're making a product to unite human and digital identities for absolute trust. And if you look, you might recognize a couple of my coworkers there on the right. If you're interested in what we're doing, check us out at vouch.io. This talk is going to be about type inference and the ClojureScript compiler. Before we get into this, it's worth pointing out that none of the stuff in this talk you really need to know. I would characterize it as things that are interesting to know. If you're trying to optimize some code, of course, it's always good to know like one level deeper. So this stuff might be useful if you're trying to do something like that. So why do we have types and type inference in the ClojureScript compiler? I mean, after all, this is a dynamically typed language. There's two reasons, and the primary one, in my opinion, is for optimal code generation. And if you think about it, we're using types to generate code in the same way that if you think about maybe the way Fortran or C use types to generate optimal code for machine language, we're doing the same thing, but for JavaScript. A secondary reason that types exist in the compiler is for type checking. And you may have seen this. If you try to add a string and a number in ClojureScript, you'll get this warning that tells you that that's not going to fly. You know, something might blow up at runtime. So that's another reason why types exist in the compiler. But I would kind of de-emphasize that. That's not really the main reason. We're not trying to turn ClojureScript into a statically typed language by having this in there. I have a dictionary as well. We'll go into a few definitions. So we're all on the same page. I like to think of a type as really just a set of values. So like, for example, the set of all strings could be thought of as a type. You could think of maybe the set of all numbers as another type. You could have subsets of these things, so you could have like all the positive numbers you could think of as another type. And you could also have like things that are like one thing or another. So something could be like a string or a number. And the composition of those two things together could also be thought of as a type. Type hinting is when you are adding, manually adding explicit annotations in your code to kind of inform the compiler, to tell it about the types that you know as a human that are in your code. You're kind of hinting the compiler to tell it what's going on. To be honest, you don't want to be getting into the game of doing type hinting if you can avoid it. It kind of makes your code a little bit more difficult to read. But if you need to, it's there. If you need to use it to optimize, you can use type hinting for that purpose. Type inference, I would say, is really just a set of algorithms that the compiler uses to deduce the types in your code without you having to tell it. So, as type inference gets better, it actually eliminates the need for you to do type hinting. And type checking is when the compiler sees that there's something that just doesn't line up, right? There might be some sort of type mismatch between things. And this is like that thing that I mentioned where like if you're adding a string and a number, type checking kicks in and it tells you that, hey, this is not good. So I thought it'd be interesting to look at the history in GitHub to see like when was type hinting or when was type inference first added to the compiler. And like the ClojureScript compiler is going on about 8 years old now. And the first evidence I could find of type inference being added to the compiler was back in around mid-2012, maybe about a year after the compiler was going. David Nolan added this unchecked if inference feature, and I'll be talking about that a little bit later. And then in late 2014, this numeric type check thing that I mentioned started to appear. Between 2014 and 2017, the type inference system improved and grew over that time. I wasn't really involved in all that. To be honest, a lot of this talk is about the stuff on the right there. In mid-2017, I put together a patch for function return type inference, and that landed in 2018. And after that, it just kind of got my gears going, and I started thinking about other things that we could add to the compiler surrounding type inference. So a lot of this talk is more about the recent stuff on the right there. We can go through a high-level overview of this stuff. Since we're using type inference to generate optimal JavaScript code, it has a lot to do with primitives in JavaScript. For Booleans, we can do this unchecked if thing that I'll talk about. I promise to talk about that. We can also use it to emit JavaScript code that directly uses JavaScript logical operators. For numbers, the compiler kind of takes the opposite stance. It's not using type inference to figure out when to do certain optimizations. It's going to go ahead and make those optimizations anyway, and it's going to emit code. Like if you're using a numeric operator, it's going to emit code that's optimal for JavaScript, and it's going to instead use type inference to then do type checking to warn you when this is not going to work. So this is that same example I bring up with type when you're adding a number and a string together. For strings, we have some new stuff recently that involves coercion elision, and we'll go into that. And there's a checked arrays feature that has a runtime component to make sure that you're passing arrays to the array functions like aget and aset. But there's also a compile time part where it checks for things, and type inference helps with that. So it'll catch when your code is going to do something that's wrong. To help understand a lot of this stuff, it helps to understand that ClojureScript has this thing called macro, or I like to call them macro functions. This doesn't exist in Clojure, per se, and this is because in ClojureScript, macros are written in Clojure. So you can have a var that represents a function that's like in the runtime namespace, and you can also have another var that has the very same name that's a macro as well. There's no problem with that. So in this little silly example here, you might have a macro named speak in a function named speak, and the macro could make like a moo sound, and the function could make a dog barking sound. They could be different. Typically, the macro, when you have one of these things, they behave in the same way. And you might ask, like, if I have these things, which one do I get if I'm using it? And the answer is that if the symbol that you're using that's tied to that var is in operator position, then that will be treated as a macro. That will be dealt with during macro expansion time. But on the other hand, if you're passing that in into a higher order function, like this map example here, really you have no choice. You can't take the value of a macro. So in that case, it has to pass the function value into that higher order function. So why does this matter for this talk? Why are macro functions important at all? They're used a lot in the core library, and the reason is that upon macro expansion time, macros have access to the compiler itself. They can talk to the analyzer. They can ask questions like, hey, for these forms, what are the types of the forms that are coming into this macro? And then that macro upon macro expansion can emit code that is optimal based on what it knows about the types that have been inferred. There's even this beast called JS star, which is used by a lot of the core macros, and it's really meant for internal use, but what it does is it lets a macro, if it wants to, emit like literal JavaScript in the end. So these macros can become highly optimal to emit like actual JavaScript that would be optimal when it comes to that runtime. So if you back up a little bit, if you tried to understand this a little, this example here is like, let's say you were trying to write the macro for the string function, and you were trying to handle this case here where you had a literal string value being passed to that. You could, in your macro code, you could have a little test to see, like, is this a string? You could use the string question mark predicate, and in that case, you could expand to directly that string. And that's like a silly little example. This is, in fact, what the ClojureScript compiler will do for this case is when it expands this, it will turn right into the string itself, and the macro will just disappear. The real string macro has a lot more stuff in it, and we'll see some of that later on. But that's a simple example just to illustrate the kind of things that you could do. So let's talk about this checked if thing. This was the first bit of inference that was added into the compiler. And in this example here, we have like a function that takes a argument x, and if it's truthy, we want to return 1, right? And otherwise, we want to return 2. If you look at the JavaScript generated for this function, it's kind of like what you would expect. The only weird thing is there's this CLJS core truth thing sitting in there, wrapping the test, wrapping the x that it's testing. If you look at what that is, it's actually a function that checks to see, is x not null, and is it also not false? The way I like to think about this is it's really handling cases like where in JavaScript, the number 0 is treated as falsy, or false in JavaScript. Same thing with the empty string. So at a high level, this is kind of like this function here is teaching JavaScript ClojureScript's notion of truth and false. And this function's pretty cheap, but the question is, if the compiler were to know somehow that x was actually a Boolean value, and that's a type hint there on the argument that basically would tell the compiler it is in fact a Boolean value, so it can only take on the values true and false in this case. If that's true, then true and false map directly to what JavaScript's going to do, so we can elide that CLJS score truth check, and then effectively turn this into an unchecked if you will. So it just saves you a little bit of performance, and that was the very first type inference thing that was added to the compiler. Likewise, there's another thing we can do with Boolean values. If we look at this function here, we have like a couple of Booleans going in, and we're doing some Boolean logic with it. We're doing and x, not y. This is the JavaScript that gets generated for that function. Looks kind of verbose, but if we follow through it, you can see that it looks like it drops x into a temporary, and then it checks using that CLJS core truth to see if that's truthy. And if so, it returns the not of y, and otherwise it returns the value that would have been x. This stuff's a bit verbose for me. I think given how small the ClojureScript was, that's kind of a lot of JavaScript that got generated. But don't despair. If you pass through Clojure, Google Clojure is the back end of the compiler. It turns into code that looks more like this. And in fact, if you're doing advanced optimizations, some of these things will even start to get inlined. So the code will get even simpler. But this begs the question, if the compiler knew that x and y were both Booleans, could it do a better job? And in this case, if it knows this, it will emit this kind of code. This is an example of those direct JavaScript operators. It's using the double ampersand for and using the bang for not. And this is, of course, a lot more compact, obviously a lot more efficient, especially if you have larger expressions like this. Having seen this, I would suggest that you resist the urge to go around and type hint all your code that you think is doing Boolean operations. If you're doing Boolean operations, oftentimes you're using predicates, and the compiler will know that those predicates return Boolean values, so you'll get these things for free due to type inference. And you really only want to do this if you're going to gain something for doing it. So this is cool, but don't go ahead and just start type hinting everything because you saw that this is the way it does it. So this is another string coercion elision. Try to say that 3 times. This is another nice thing that we have that's actually fairly recent. And we have, in this example here, we have a function that returns a string, and we're interested in the performance of this expression that's in the middle of this simple benchmark form here. So if we focus on that expression itself, and, it's concatenating the name of the local that went in there, this hyphen, and the call to that foo function. If we look at the JavaScript that gets generated for this thing, if you back up and look at that, what it really is it's a JavaScript array that's being joined with an empty string. So that's how we get our concatenation out of this thing. The hyphen drops directly in there because the compiler knows that that's a literal string. But then you have these other long-looking function names that are in there. You have to say, what are those? They actually are static dispatch calls to the singularity string runtime function. But what that gets for us is for whatever you pass to that, it will turn it into a string. So for example, if you had a number, you get a string back out of that. And these are the coercions that we're worried about. And in recent versions of the compiler, it will now know that name returns a string, and it'll also know that that foo function returns a string. So what happens is it takes those coercions out. They're unnecessary, and you can just have simpler code like this, much more compact. If we take this thing that we were focused on and put it back into our benchmark, and this will run it umpteen million times, and we'll see like the overall performance. If we compare that to previous versions of the compiler, we get pretty good performance speed ups. You could argue that this is a micro benchmark, but to me it's kind of good to know that all throughout your code, you're getting this background noise of performance stuff being eliminated. So that just showed a little bit of performance measurement. How do you do this? For me, if I'm at the REPL and I have a form that takes a while to run, we all know this, you can just apply time to it, and you can get the amount of time that it took to evaluate that expression. But if the form you're evaluating is really short, you may want to loop over it several times to see how long it takes. So take an example like this, where you're letting a map, and you're interested in the performance of, how much does it cost to use a keyword to extract a value out of that map. There's a thing built into ClojureScript called Simple Benchmark. It's in the core library. And all you have to do is call it this way. It looks like a let, and you just have to add the number of iterations. And what that'll turn into is a loop. It'll run it that many times, and it'll tell you the total amount of time that it took to run this thing. So in the ClojureScript compiler, we have a setup where we can run this kind of stuff over all the JavaScript VMs that you have configured on your box. And I don't know if you're like me. I can't predict these things. My intuition on performance is horrible. So I have to run these things, and to this day I'm still surprised how often I get it wrong. So when I run these things, you have to run it, and you find it oftentimes the fastest engines tend to not improve when you're making performance optimizations. It's almost as if they are really clever and they've figured out all the tricks, and they're already doing all the stuff already, and it's really the slower engines that tend to improve when you add a performance optimization. So if you're interested in doing this kind of stuff on your own code, this is kind of nice. I wrote up a blog post, ClojureScript Performance Measurement, that kind of details how you can use the setup that the ClojureScript compiler is using to do the same kind of testing. Okay, so let's talk about the type system itself. There is a very popular one called Hindley-Milner. It's popular for functional languages, and it's had a lot of proven properties that are great for it. ClojureScript does not use the Hindley-Milner type system. How about the Hickey-Miller type system? I think these guys are more interested in this spec thing they have going on, so it's not that either. Looking at the GitHub history, I think it's largely due to David Nolan. He's the one who at least started it off. Of course, a lot of people have contributed to make it grow over time, but I would say largely he's the one that kind of made it take its shape that we know. So what is that? What is the type system? So if you have a thing that is Boolean, so you have like the exactly two values for it, true and false, in the ClojureScript compiler, that is represented with the symbol Boolean. Likewise, if you're talking about something that could be the set of all numbers, that's the symbol number and string for all strings. And then there's the case where you might have something that could be, say, like a Boolean or a number. That is represented in the compiler as a set of the symbols that we're representing. There are a few other symbols that are meaningful to the compiler. One of them is the any symbol. So if you think about like the identity function and you ask like what is the type of the argument to the identity function, that concept is represented by the symbol any in the compiler. If you're looking at the types that the compiler has inferred and you run across a situation where you see that it's nil, that's a little bit different than any. That philosophically does not mean that it could be anything. To me, it really means that the compiler just hasn't inferred it, whatever it is. It could be a numeric type, just don't know. So that's more like an unknown thing. So let's say you do happen to know that the type of something is nil. That's represented by this funky symbol CLJ-nil. And as an interesting aside, the notion of nil in ClojureScript is implemented by both null and undefined in JavaScript. Both of those are aliased together into this single notion of nil in ClojureScript. That has nothing to do with the type stuff, but it's just kind of an interesting aside to know. So you might ask, like, well, why don't we just do quote nil to represent this type? And part of the answer is if you do that, you get back nil, right? So, well, what if you did symbol nil? You just forced the issue. And this is kind of evil too, because if you did this, then you can't really see the difference between this. Unless you have some sort of system that's color coding what you're seeing, they would look the same. There's another interesting type symbol in the compiler that is meaningful to it, and that has to do with the type of the things that come out of the seek function. So, if you think about the seek function, it can return either nil if you pass in something empty to it, or an actual sequence that's non-nil. And this turns out to be incredibly useful in the system, because you oftentimes have code that will look at the truthiness of the return of the seek function to know whether or not you should keep iterating on something or something like that. So this is built into the compiler, and that's the way it deals with that notion. So as the compiler is going along and it's composing types that it's inferred and working on things, at certain points it's useful to be able to compare types. So there's a few type canonicalization algorithms in the compiler. And one of them is simply if you have a singleton symbol like this, that gets turned into just the symbol by itself, string. Similarly, this is kind of a silly example. If you have something that ends up being any or something else, that could be canonicalized to just simply being any by itself. And since the seek function can return nil, the type seek itself kind of encompasses the notion of nil already. So if you have something like this, that'll be canonicalized just down to seek by itself. So this, that's the type system. It's pretty simple. You have symbols to represent things, sets of symbols. You have a few symbols like any and seek that have special meaning in the compiler. But it kind of reminds me of maybe the corollary to Greenspun's 10th rule. Inside the compiler, we have a very simple type system going on in there. So if you haven't seen type hinting, type hinting is the way you let the compiler know about types, and it's based on Clojure's meta system, right? So you can apply meta to various things like symbols, vectors, and whatnot. And what this means here is if this were to precede, say, a symbol, if you have a caret preceding a keyword, this is shorthand for applying a meta map that's a singleton map containing a keyword foo and the value true. Similarly, if you have a caret preceding a symbol, what that actually means is the keyword tag and the value foo. And where that's important for this is that tag to Clojure and ClojureScript means type, essentially. So this is how you type hint types. And one little twist to be aware of if you're comparing Clojure and ClojureScript, if you type hint a function, you'll get, in ClojureScript, you'll get a tag with the value being the symbol foo, as opposed to what you would get evaluated if you were doing it in Clojure. And that just has to do with the way ClojureScript works. And also this kind of lines up with the fact that, like we talked about, all the types are various symbols, like Boolean, string, whatnot. So let's talk about some of the type inference algorithms. The simplest one to start off with is what I would call an inward flow algorithm. In this bit of code here, the compiler is smart enough, it sees that number 1, it can infer that that's a numeric type. But where it starts to get interesting is that it then knows that x is also a number, and then it knows, since you're binding y to x, it knows that y is also a number. And in the end, in that innermost form there where it's adding y to 3, the compiler knows that you're adding a number to a number. That's a good thing to do, and the compiler's happy. On the other hand, if you take the very same thing and instead bind a string to x, that will flow all the way down to the innermost form, and the compiler will actually see that, and it will emit one of these type check warnings, and it will say, hey, you're adding a string to a number, that's not good. If you look at this little bit of code here, you can ask the question, what is the type that the compiler would infer for this entire form here? We don't know what this predicate's going to do, but if we're just analyzing this, you know that it could return true, or it could return the number 11. So this is an example of where the compiler will infer a thing that involves a set of symbols. And that's one of the ways where this comes into play. Return type inference is actually a relatively new feature. It only landed within the past year. And the way it works is the compiler looks at the body of the function there. And in this case, the string macro, when it expands to a form that has a tag string as meta. on it. So that's how the compiler knows that the body of this function returns a string. And with this feature, it's as if you had manually hinted this thing to return string. If you look at this expression here where we're adding a call to that function and the number 1, previously, if you were to compile this, the compiler would just compile it for you. And now with this new feature, it now knows that there's a problem and it'll warn you for this kind of code. One nice thing about this is that if you're writing predicates, oftentimes the compiler can look at the body of your predicate and it can infer that your predicate returns a Boolean. And if that's true, then as you're using predicates in your code, you end up with the unchecked ifs that it can do and some of that other stuff I showed with logical operators being used directly. Unfortunately, this leads to another problem that I'd like to call calcification, and I'll talk a little bit more about that later on. Another cool inference algorithm is something we call predicate-induced inference. And to understand this one, if you look at this bit of code here, you can ask the question, what is the type of the symbol x in that innermost form? If you look at that, you know in order for the flow of control to have reached that point, x had to have satisfied the predicate number, right? So that essentially, the compiler essentially then assumes that type is number, and of course that type checks properly. This feature is actually cool in that it's baked into the if special form. So the way it works is if you have a test that involves a fairly simple predicate against a local, then in the then branch of that if you ever use that local, you'll get this kind of type hinting implicit to it. And in the else branch, it doesn't affect the else branch at all, or the then branch. This, unfortunately, only works for core predicates that are in the compiler, because this is kind of hard-coded into the compiler. It knows about number and string and other common predicates that the compiler knows about. Okay, let's talk about another type inference algorithm, loop recur widening. I don't know if you're familiar with spec. There's this function called instrument, spec test instrument. And there's this awesome other function that goes with it, like the opposite is spec test instrument. I think that name is genius. For loop recur widening, we have type inference, and for this, we're going to need type inference. So if you look at this bit of code, you can ask the question, like, what does this whole thing evaluate to? If you look, it's going to be whatever x in that innermost x evaluates to. Previously, the compiler would treat this loop as if it were a let. It would basically infer that x is a number. And that's just not right for this bit of code, right? So we need our little bit of inference, and what the compiler will now do is it'll widen the type that it infers for this, and it'll add string to that. And that'll happen, of course, if that predicate is evaluated to false. It recurs, goes to the bottom, recurs, and then comes back around and turns x into a string. This kind of code is another common pattern, I think. It's, Clojure and ClojureScript are dynamically typed, so it's often like you have a loop recur and you don't know the value that you're going to produce. So you initialize a loop bound thing to nil, right? You just want to set it up. So in this case, if you looked at what the old compiler would do, it would infer that this whole thing is just the CLJ nil type, and that's not cool. And if you do your inference thing and you add string to that, you have to ask, is that even right? That's an improvement, but is that even correct? You have to ask, like, how could this thing return nil? Nil is falsy. So you could evaluate this in your REPL, and you'll see that it's going to return a string. There's no way for nil to come out of it. So what, in fact, the compiler will do for this thing is it'll just return string as being the inferred type for this entire expression. So how did that work? How did it do this? There's another inference algorithm that's fairly recent in there, and if you look at this bit of code here and you ask, if you knew that the type of X involved perhaps a set of different things. It could be a Boolean, it could be nil, or it could be a string. Well, in this particular case, if you ask what is the type of X in the then branch of this if, it can't be falsy, right? So what the compiler is going to do is eliminate that CLJ nil from the type and then deduce that it's just a Boolean or a string. Okay, so calcification. This was the problem that I mentioned with return type inference. Let's say we have a function that returns a Boolean, and we're going to use that function. In a function, we have to call it bar, of course. And this is the JavaScript that would be generated for that function. And as you can see, the JavaScript that gets generated in this case directly tests the return value of foo. It's an unchecked if in this case. And let's just say you call that function you call bar with the empty string. And if you look at what's going to happen here, foo is going to return true. So this whole thing, that's going to evaluate to the number 1, right? What if in our REPL we redefined foo to now return the count of its argument? And then we ask the same question, what does bar return now? In this case, bar, the count of an empty string is going to be 0. If you look at the JavaScript, 0 is false in JavaScript, so it's going to return 2 in this example here. That's not the right answer. So one way you could look at this is that the compiler kind of has, some stale code that it's generated based on a type that is no longer true. We don't have a solution for this right now in the ClojureScript compiler. This only affects the REPL. But we do have another problem that's similar to this, where it has to do with static functions. And what that's about is if you have a multi-arity function, the ClojureScript compiler will generate static dispatches for each arity, along with like a part at the beginning that routes it to the right one. And there is an optimization that the compiler can make where if it knows the arity of the function that you're calling, it will directly emit a static dispatch to the one that matches that arity. That's bad for the REPL if you're redefining your multi-arity function, and you may end up with code that's calling a static dispatch that no longer exists. So the way static functions works is the compiler, the tooling, by default, the static functions thing is set to false at REPLs. So that optimization is basically turned off. And it's really only enabled by default for advanced builds, essentially. Another thing that can go wrong with all this type inference stuff is that the type inference algorithms they're not free, right? They tend to be fairly cheap, but they're not free to do. So we're always measuring the performance of the compiler. This shows how long it takes to compile the coal mine corpus of code, which is like a quarter million lines of code. And as you can see, like as release goes by, we've improved it, especially between 110.339 and 110.439. There was a lot of optimizations, and that's just general performance optimizations that have been made. So it'd be unfortunate if we came along with a clever type inference algorithm that just kind of botched this performance. So far, we've been pretty lucky. All these type inference algorithms, it's been impossible to optimize them to get them down to like a performance hit of maybe like 1 or 2% slower. So it's like a trade-off, and you're like, this is worth it. Let's put this in there. So if you're interested in types in your own code, you're curious to see like what the compiler is inferring for your code. I have a little library, and it's just one macro. And what it does is that thing that I mentioned. It talks to the analyzer, and it asks the question, like, what is the type of the form that you pass to it? So you can use this to, if you say, what is the inferred type of this expression here? And it'll tell you that it's number. It won't show a picture in your REPL, but it'll tell you that it's number. You can also, since this is a macro, you can put it down inside of a form somewhere, and when you evaluate that, it'll return, in this case, string. And one thing, if you didn't know, this is just an aside, if there's tools like this that you'd like to use in your REPL, you can now put stuff like this and other things like this that you'd like to use at dev time in your user CLJS file. And if that's on your class path, the compiler will pick that up and load it into your REPL. This is just like the same feature in Clojure if you put something in user CLJ. So that's the stuff that exists, and we can now go through some of the experiments that we have in various patches and see what could be in the future. So one of the ones I like to call specializations. If you think about the count function, it has inside of it a bunch of runtime checks to look at the actual value of the argument passed to it. So like if you pass nil to count, you'll get 0. If the thing that you pass to it implements the iCounted interface, it'll call dash count on it. If it's a string, it'll get the length of that string. If it's an array, it'll get the a length. Things like that. But all that's at runtime. So it kind of begs the question, if we knew that what you are passing to the count function was either a string or an array, if we knew that at compile time through inference, could we just instead emit a call that would access the length property on this thing? And there's a patch, and if we do this, you get like anywhere between 10 and 6,300% performance improvement. So that's pretty cool. Direct field lookup, this one's kind of cool because it involves something that's not even a JavaScript primitive. This is if you make a def record and you want to use a keyword to to access a field in the def record. The compiler can infer that X is of this record type. But if you look at the code that gets generated for this, you have, it looks pretty verbose, but to be honest, keywords in ClojureScript can get thrown into the constant pool. So effectively, this thing that constructs this keyword would be pushed up into some higher level point, and at this point in the code, you would essentially get a reference to that. And keyword lookups on records are already pretty optimal in the sense that they involve a JavaScript switch, so it's like an order 1 lookup to get to that field. But this also begs the question, if the compiler knew this, could we just emit code that says x.a, right? And in this case, you get some pretty healthy performance improvements as well, 66 to 450% faster. Another one is REST Args inference. This one seems kind of silly, but if you think about it, I actually noticed this. If you look at the code for the struct function, the runtime struct function, there's an if that kind of looks like this in there. And in this case, you could argue that the x's that's in a REST args could be inferred to be of type seek, because it's either going to be nil or some sequence. So there's an experiment that has this kind of patch that does this, and what it effectively does for this case is it turns this kind of code into an unchecked if. So you gain, you eliminate that CLJS core truth that would have been in there otherwise. Parameter type inference is another interesting experiment, and in this case, the result would be to infer the parameter s to this function. I actually saw some code like this in CLJS preprint that looked like this. And here's the code that gets generated for this expression. And it has like a coercion in there. And if you look at what Clojure will do for you, Clojure will turn the substring, or it'll basically inline that substring call. So that already gets bettered just by using Google Clojure. But there remains that coercion sitting in there. And if you look at this code, since s is being passed to the substrings function, you know that it has to be a string. If you pass anything else to subs, your program's just simply invalid. It has undefined behavior. If you try it in Clojure, you're going to get an exception. So this code's not going to work. So that implies that s is a string, and then we could, from that, effectively infer that the type of the argument of foo is a string. We can infer that parameter type, and therefore we know that the s on the left there is also of string type, and we can get rid of that coercion in this case here. In this experiment, there's a bit of code that, since it's doing parameter type inference for functions in general, the numeric functions in ClojureScript kind of have hard-coded into them the fact that they take numbers. This would be like a general capability. So in that same experiment, it does type checking. So like if you write your own function and it can deduce the parameter types, and then from another function you call that one and you pass the wrong types in, it would do a type check and warn you about that. To be honest, we're probably not going to do this in ClojureScript because there's better ways to do this kind of stuff. We now have spec that you can use to spec your parameter types. And in fact, if you have specs, another thing that we could consider doing is looking at those specs, and if they're simple enough, we can then deduce the parameter types directly from the specs. All right, speaking of Clojure, some stuff that we could do with it. David Nolan did an experiment where he found that it's pretty easy to glean the types of values from the Clojure libraries. Like there's a lot of low-level libraries that we're using, and those have type information in them. So the idea there is that we could inspect that stuff and then use that as another source for type information that could then flow throughout your code through type inference. Another thing I think we could do better is we could probably, since we're inferring types, we could add those to the code that the ClojureScript compiler is generating so that Clojure could then leverage those types that we put in there to do better things. Some other uses for this kind of stuff. Externs inference is a feature that will automatically infer externs when you're calling other libraries. This is a thing that has to do with advanced compilation. What's germane to this conversation is that sometimes in the externs inference feature, you have to manually hint a certain JavaScript type in there. And the argument is if we get better and better at type inference, then the amount of manual type hinting that you have to do decreases. You can get by with fewer type hints because inference lets things flow to new places. Same thing is true with the checked arrays feature. As there's a synergy here where as inference gets better, any of these things like checked arrays or numeric type checks, they all just get better as type inference gets better. And then another really cool, exciting use of this stuff is something that Kevin Lina was doing. He has some code that will take Hiccup and generate code. It's macros that generate code that interacts with React. And by default, a lot of those macros would expand to code that would do runtime interpretation of things. And essentially the idea here is if those macros knew that, say, for example, a certain element was of type string, then it could eliminate that runtime interpretation and it's kind of like elide that stuff. And you just get these drastic performance improvements. So if you're interested in what he's doing there, he has a cool blog post on that on fast ClojureScript React templates. I would suggest you go check out that. To me, that's exciting because it's the first time I saw like types being used outside the compiler. He's calling private API to pull this off, but awesome. It's like he's leveraging this stuff that the compiler has outside of it in another library. So one way I'd summarize all this, if you recall, David Nolan gave a talk where he talked about the next 5 years of ClojureScript. That was maybe like 2 or 3 years ago that he gave that talk. Nowhere in there did he talk about type inference as being part of the next 5 years of ClojureScript. But he did say that like things are a random walk in the right direction. And this was definitely, I feel like a random thing that happened, and hopefully it was in the right direction. And I would emphasize again that all this stuff, you don't need to know this stuff in order to use the ClojureScript compiler. You can just use the compiler, but if you really, if you have some code that you need to make fly, this is an awesome set of tools to know about how things actually work at that next layer down. All right, thank you for watching. Thanks. So it looks like we're about 40 some odd minutes in, so I think we have time for questions. There's one, yeah.
I was wondering if you could confirm something that I think might be true, this difference between Clojure and the ClojureScript compiler with for. So my understanding, it's a bit simplification, is that the type hints in Clojure are kind of like advisory for the reflection system.
Yes, yeah.
Largely. I mean, there's some issues of primitives, but and it seems like here they're actually more active. Like they're actually changing the code that comes out in a way that is different. Like,
I think, yeah, that's a good observation.
Like if I put the Boolean in and it's not supposed to have one, then it's bad, right? And
yeah, so there is that fact where I think what you're pointing to is that maybe in Clojure with a type hint, you can't cause it to break things, right? Yeah, that's true. I actually talked to David Nolan about this subject and straightened out my own thinking on it, and it is exactly what you're seeing. When you type hint something, that, especially in the ClojureScript compiler, it's taking your word for it, and it's going to use that to emit code that would be wrong if your type hint were wrong. Yes, That's a great observation. Yeah. Mm-hmm.
Hey. So you said that user-defined macros can talk to the analyzer
Yes,
and
yeah.
make expansion decisions based on analysis.
Yes, yeah.
Does that effectively mean that the analyzer's API is part of the public API?
No, it's a private API, so if you do that, yeah, there's chances of breaking. But I think the intent would be, like, if that becomes a popular thing to do, then that would probably be put into some public API that's guaranteed to be stable. Yeah.
Thank you.
Mm-hmm. All right, sounds like that's it. All right, thank you. Mm-hmm.